Section: Introduction. In this section, we discuss how, despite the impressive achievements of deep reinforcement learning (RL) in solving real-world problems, there are emerging challenges and issues during the training of these networks. It has been observed that deep RL agents often do not fully utilize their network's parameters. This underutilization is evident in several ways. There's an implicit underparameterization. A significant number of neurons become inactive during training, and it has been found that sparse training methods can still achieve good performance using only a small fraction of the original network parameters. One particularly interesting discovery is that by applying a technique called gradual magnitude pruning to a DQN model with a ResNet backbone, performance can be improved by 50% while only using 10% of the original parameters. However, when this pruning technique is applied to the original CNN architecture, there's neither improvement nor decline in performance. This suggests that the impact of pruning depends on the underlying network architecture, indicating that using non-standard network topologies might be beneficial for training deep RL agents. In our paper, we explore gradual magnitude pruning as a technique to enhance the performance of RL agents. We find that this technique not only improves the performance of standard network architectures but also shows that the benefits increase with the size of the base network architecture. This is particularly important because deep RL networks often struggle with scaling up. Our main contributions include presenting gradual magnitude pruning as a technique for maximizing parameter efficiency in RL, showing that networks trained with this technique produce stronger agents, demonstrating the technique's usefulness across various agents and training regimes, and providing in-depth analyses to understand the benefits of this approach. Related to our work, scaling deep neural networks in RL has been a challenge, similar to the scaling laws observed in supervised learning. This difficulty is partly due to training instabilities unique to RL. Recent studies have managed to scale networks successfully by using targeted techniques and careful selection of hyperparameters. Some have switched from CNN to ResNet architectures, which are more scalable, and others have found benefits in increasing the number of features in each layer of the ResNet architecture or employing spectral normalization and reducing batch sizes to mitigate training instabilities and enable scaling. Sparse models in deep RL have also been explored, with previous studies using knowledge distillation, policy pruning, and the exploration of the lottery ticket hypothesis to achieve sparsity without sacrificing performance. Dynamic sparse training methods, which allow the sparse topology to change during training, have shown significant advantages over static methods. Techniques like delayed multi-step temporal difference targets and dynamic capacity replay buffers have enhanced the effectiveness of dynamic sparse training. Lastly, the issue of overparameterization in deep RL, where networks tend to overfit or lose plasticity, leading to a decline in performance, has been addressed. Strategies like data augmentation, dropout, layer and batch normalization, and weight regularization have been proposed to mitigate these issues. Some studies have suggested periodic network reinitialization or reinitializing dormant neurons to improve network plasticity and facilitate continuous learning. In summary, our exploration into gradual magnitude pruning reveals its potential as a general technique for improving RL agent performance, especially as networks scale. Our findings contribute to a deeper understanding of how to efficiently utilize network parameters in deep RL and open up new avenues for research in network topology optimization. Section Summary. In this section, we introduce gradual magnitude pruning as a technique to enhance the performance of reinforcement learning agents by maximizing parameter efficiency. We demonstrate that networks trained with this method outperform their dense counterparts and show a scaling law where gains increase with the size of the initial network. Our analysis suggests that training deep RL agents with non-standard network topologies, induced by techniques like gradual magnitude pruning, could be beneficial and warrants further investigation. Section: Deep Reinforcement Learning. In this section, we delve into the realm of deep reinforcement learning, where our main objective is to maximize the total reward over time, which is often described through a framework known as a Markov decision process. This process involves a set of states and actions, along with a model that predicts how actions lead to different states, a way to calculate rewards, and a factor that discounts future rewards to prioritize more immediate ones. We also define a policy, which is essentially a strategy that dictates the actions an agent should take. The effectiveness of a policy is measured by a function that estimates the expected rewards from following it after taking a specific action in a given state. The ultimate goal is to find the optimal policy that maximizes these rewards. To achieve this, modern techniques often approximate this function using neural networks. This approach was pioneered by the development of the DQN agent, which has influenced many subsequent algorithms in deep reinforcement learning. These networks are trained to predict rewards using a method that compares the predicted reward to the actual reward received, adjusting the network to reduce errors. The training process is supported by a replay buffer, a collection of past experiences used for learning, and a secondary network that helps stabilize the training targets. Enhancements to the DQN algorithm include various strategies like double Q learning and prioritized experience replay, among others, which have collectively improved the performance of these agents. Moving on to the concept of gradual pruning, we explore how it's applied in the context of supervised learning to enhance efficiency. The idea is to reduce the complexity of a neural network by systematically removing the least important connections, based on the magnitude of their weights, over the course of training. This technique not only reduces the computational load but also speeds up the decision-making process. We apply a specific schedule for pruning in deep reinforcement learning networks, starting at a point early in the training and concluding it before training ends, aiming for a significant reduction in the network's complexity. We investigate how this approach of gradual pruning affects the performance of deep reinforcement learning agents in various scenarios. For our experiments, we utilize the JAX versions of the DQN and Rainbow agents from the dopamine library, along with a specific neural network architecture known for its effectiveness in these applications. We adhere to a pruning schedule that significantly reduces the network's complexity towards the latter part of training. Our experiments are conducted on a diverse set of games within the arcade learning environment, focusing on a manageable number of game frames to ensure computational feasibility. The performance of our agents is evaluated based on their ability to match or exceed human-level gameplay across these games, with results indicating the potential benefits of our pruning strategy. All of our experiments are rigorously designed to ensure reliability and are executed on high-performance computing resources, taking into account the time and computational power required. Section Summary. In this section, we delve into the realm of deep reinforcement learning, where the primary aim is to optimize long-term rewards through Markov decision processes. We explore the concept of gradual magnitude pruning in deep RL networks, showcasing its potential to enhance performance in both online and offline scenarios. By gradually sparsifying dense networks during training, we observe improved results in deep RL agents, shedding light on the significance of this technique in enhancing computational efficiency and inference speed. Section: Online RL. In this section, we explore the concept of online reinforcement learning, RL, and how sparse networks, which have a reduced number of active parameters, can still maintain or even improve the performance of agents. We start by examining the effects of applying gradual magnitude pruning, a technique for systematically reducing the number of parameters, to the Deep Q network, DQN, with the Impala architecture. Specifically, we increased the size of the convolutional layers by 3 times. Our findings show that at 90% and 95% sparsity levels, there is a 33% improvement in performance, and even at 99% sparsity, the performance is maintained. Interestingly, a sparsity level of 95% consistently delivered the best results in our initial tests, leading us to focus on this level for further investigation. We observed a remarkable improvement in performance when comparing the pruned and scaled networks to the original, unpruned, and unscaled architectures. Specifically, we saw up to a 60% improvement for DQN and a 50% improvement for Rainbow, another RL algorithm. Unlike the unpruned architectures, whose performance decreased with increasing network size, the performance of their pruned counterparts improved. This trend was confirmed across all 60 Atari 2600 games, indicating that our findings were not limited to the 15 games initially selected. When we reverted to using the original convolutional neural network (CNN) architecture for both DQN and Rainbow, we noticed a similar trend for Rainbow but little to no improvement for DQN. This aligns with previous research indicating that pruning does not significantly benefit CNN architectures. However, we did observe that increasing the network width improved DQN's performance, while slightly degrading Rainbow's performance. These observations suggest that gradual magnitude pruning enhances the efficiency of these agents, potentially allowing them to benefit more from gradient updates. We tested this by examining the replay ratio, which measures the number of gradient updates per environment step, and found that pruned architectures indeed maintained their performance advantage even at high replay ratios. In the context of a low data regime, we evaluated our pruned agents using the Atari 100K benchmark, which limits agents to only 100,000 environment interactions. Despite seeing no initial gains, significant improvements were observed when the agents were allowed 40 million interactions, especially with the use of gradual magnitude pruning. Notably, in the DRQ variant, pruned agents avoided the performance degradation seen in the baseline when trained for extended periods. Turning our attention to offline RL, where agents learn from a fixed dataset without interacting with the environment, we employed two recent methods, CQL and CQL plus C51, with the ResNet architecture. Training these agents on 17 Atari games for 200 million frames showed that pruned networks, particularly wider ones, significantly outperformed their unpruned counterparts. Pruning also prevented performance collapse in shallow networks and, in some cases, even improved performance. Lastly, we investigated the impact of gradual magnitude pruning on policy gradient methods, specifically the soft actor critic, SAC. Our evaluation across 5 continuous control environments from the Mu-Jo-Co suite revealed that the benefits of pruning persisted in 2 environments, while in the remaining 3, no significant gains were observed. In summary, our exploration into online RL, low data regimes, offline RL, and actor-critic methods demonstrates the potential of gradual magnitude pruning to enhance the performance and efficiency of reinforcement learning agents across a variety of settings and architectures. Section Summary. In this section, we explore the impact of gradual magnitude pruning on reinforcement learning agents in various settings. We find that scaling the initial network can enable high levels of sparsity, leading to significant performance improvements in both DQN and Rainbow architectures. Additionally, our findings suggest that gradual magnitude pruning enhances parameter efficiency and allows sparse networks to benefit from more gradient updates, maintaining a performance lead even at high replay ratio values. Section: Stability of the pruned network. In this section, we delve into the stability of networks that have undergone pruning. We adopted a pruning schedule that adjusts well to different lengths of training, a method we previously discussed in the context of offline reinforcement learning experiments. Specifically, this approach involves training the final, sparser network for just the last 20% of the training steps. A question that naturally arises is whether this sparsely trained network can still perform well if trained for a longer period. To answer this, we trained a deep Q network, DQN, for 100 million frames, applying both the regular pruning schedule for 100 million frames and a condensed schedule designed for 40 million training steps. Our findings, illustrated in the referenced figures, show that the network retains its strong performance even under the compressed schedule. In fact, it reaches higher performance more quickly than with the regular schedule, suggesting that exploring alternative pruning schedules could be beneficial. Why does pruning work so well? We focused our analysis on 4 video games: Beam Rider, Breakout, Enduro, and Video Pinball. For each game, we looked at several metrics: the variance in the Q value estimates, the average size of the network parameters, the average size of the Q values, the effective rank of the matrix, and the proportion of inactive neurons. Our results, summarized in the figures, reveal that pruning not only reduces variance and the size of the network parameters but also decreases the number of inactive neurons and increases the effective rank of the parameters. These effects could be due to a kind of normalization or perhaps because the network becomes more adaptable. When comparing pruning to other methods, we aim to separate the effects of pruning from those of normalization and direct enhancements to network adaptability. Regarding normalization, we considered two types of L2 normalization known to be effective: weight decay, which penalizes large weights, and a specific L2 regularization that maintains the weight norm at 1. To address the loss of adaptability, we compared our method against two recent approaches. One approach resets the network periodically to counteract overfitting, a strategy found to be quite effective. Another method recycles inactive neurons throughout training to maintain network expressivity. Our comparisons, as shown in the figures, indicate that gradual magnitude pruning outperforms all other regularization methods throughout training. Interestingly, increasing the network's width generally leads to worse performance for most regularization methods, suggesting that the benefits of pruning are not solely due to normalization or increased adaptability. However, our further analysis suggests that increased adaptability does result from pruning. The impact of pruning on adaptability is significant. Adaptability, or plasticity, is crucial for a neural network's ability to adjust quickly to changes in data distributions, especially in the non-stationary environment of reinforcement learning. Yet, reinforcement learning networks tend to lose this adaptability over time. We examined the structure of gradient covariance to understand the network's loss landscape better and found that improved performance and increased adaptability are often linked to less gradient correlation and reduced interference. Our observations, supported by gradient covariance heat maps, show that in denser networks, gradients tend to align closely, whereas this alignment is much less in pruned networks, indicating a reduction in gradient interference.